Hi guys, sorry for that interruption. I made an error, and so I trimmed that part of the stopped that video and trimmed that part of it, and so I'm kind of starting over with this one, picking up where I left off, talking about the C values. Right. So we said that going back over here that C equals Kr over Kt, and I went ahead and gave you the definitions of Kr and Kt previously, right? Kr is the tendency of the R form to release its substrate, and the Kt was the tendency of the T form to release its substrate, right? And so we said that the T form really doesn't like substrate very much at all. And so usually the Kt is going to be really, really high, and usually the Kr is going to be really, really low because it really likes substrate. It really likes to bind it. So C is going to be pretty much always a low number, right? Now, from enzyme to enzyme, though, it's not always the same. Some of them will have slightly different C values, and this can affect their activity. And so if you go to this, go back to this photo, and it's part B that shows the C values along with the activity curves. You can see what the effect is. All right, so let's say Kt was just infinitely high. It had absolutely no tendency to want to bind a substrate at all. And so it had all the tendency in the world to release it. And so in that case, Kt is essentially infinite, and that makes your C value, for all intents and purposes, 0, right? In cases like this, that's where you really see more of the cooperative effects, right? The curve, the blue curve here, is more sigmoidal than the other two. As this ratio increases, though, and you can see it never gets high. We have two other ones, C equals 0.04, C equals 0.1. But even this change can, alter your activity a little bit. You notice as the C value increases, the curve gets less sigmoidal and more hyperbolic, right? So there's basically a couple of different factors with allosteric enzymes that can play an impact on their activity and their activity curves, right? You see more cooperative effects and a more sigmoidal curve when your C value is at its lowest and when your L value is at its highest, and vice versa. All right. All right, so one thing we haven't really discussed yet is inhibitors and activators, right? All that we've looked at so far is what happens just when a substrate binds an enzyme, right? In the concerted model, R form is the one that likes to bind. Substrate comes in, it binds to it, takes it out of equilibrium. You got to make more of it, right? So that's how we see the positive cooperativity. Well, we haven't looked at activators and inhibitors yet. All right, so this photo here, with the one with the pink, shows what happens whenever you have an activator or inhibitor. I want to draw a little bit more of a simplified version. Where did my little home button go? Oh, weird. Whatever. There we go. Okay. I want to draw a little bit more of a simplified version to maybe get you started, and then you can use this one, which is artistically much better than what I can draw, but I'm going to do this one anyway. All right, so let's say we had this. All right, this is an R form of an enzyme. And then we have the T form. The inactive form. Okay. So, let's add an activator. Okay, so this is going to be the active site for substrate. All right, so that's where the substrate binds in the R version, but we do have another place over here, right? This is a binding site for an activator. So an activator can come in and bind. Right? And guess what? It's doing the same thing as a substrate would have done, right? It's binding to this R form and taking it out of this equilibrium with T. According to Le Chatelier's principle, again, we got to convert more of this T back into R, right? So this is where we see positive cooperative effects with an activator because, just like with a substrate, it can bind and take that R form out of equilibrium. All right? I'll see if I can just rewind here without having to erase and start over everything. Son of a nutcracker. Oh well. I tried. All right. So let me draw this again. Hopefully I can remember what they look like. All right. What about an inhibitor? All right, so inhibitor is going to make the enzyme less active, right? It's going to have negative cooperative effects. Well, what does that mean? Well, what's the inactive form? What's the part that doesn't like to react? That's the T form, right? So an inhibitor is, wow, I just butchered the spelling of inhibitor. That's so embarrassing. Sorry. An inhibitor, God, I cannot think today, guys. Sorry. There we go. An inhibitor is going to remove T from the equilibrium, so you have to convert more of your active R form into the inactive form. So let's say we had, I don't know, something like that. It looks like a fang. And this inhibitor bound to the T form, right? It would remove it from equilibrium, and more of your R form has to go into the inactive T form. Right? So really all of this is just playing with equilibria and learning how Le Chatelier's principle is going to shift the equilibrium to either the active form or the deactivated form. Okay, and if you look at this plot, activators and inactivate, and I'm really kind of used to organic chemistry saying activator, deactivator for like aromatic reactions, so I'm trying to get back into biochem mode here. Activator, inhibitor. All right, so again, we kind of have this pattern of you having sort of a baseline activity curve, that's the blue one, where you have a sigmoidal plot, and then either the curve getting more sigmoidal or less sigmoidal depending on what's there. When you add activator, it tends to convert so much of the inactive form into the active form that for all intents and purposes it displays Michaelis-Menten kinetics at that point. Right? The curve is very hyperbolic. However, you add inhibitor and the curve becomes much more sigmoidal, much less activity at the beginning, and takes you a lot of substrate to get up to a higher velocity. Right? All right. Very good. That is the concerted model. Then the second model is the sequential model. And like I said, if the concerted model is the whole enzyme changing conformation at one time, the sequential model is basically the same thing, except it sort of does so sequentially. Well, that's where you get the term from, right? Subunit by subunit by subunit. So each individual subunit can have T and R forms. All right. A binding of a substrate will induce a conformational change specifically in that subunit, and then that conformation change can make other subunits more easily change conformation. All right. As you might expect, just like with a concerted model, activator binding favors the R form, and inhibitor binding favors the T form. I don't have a diagram of this in the PowerPoint, but there is one in your book. If you want to look at it, it's on page 172, figure 7.7. But really, basically, it's kind of showing the same thing that we were showing before, just within an individual enzyme and individual subunits. So we're not going to really see dramatic differences in activity curves or anything here as opposed to concerted model. It just happens sort of bit by bit instead of all at once. What is useful to go over is to look at how we can activate or deactivate enzymes, either in the sequential or the concerted model. There are many, many different ways of doing this. We already talked about, one way, the feedback inhibition loop, where you have a product that comes back and can inhibit the enzyme of a step in the pathway that occurred before. Other ways that you can do this. A lot of times, it's by just modification. You might covalently modify a certain group, like an amino acid, for example, that's on a chain, by taking a group away from it, a group of atoms away from it, or adding it to. Phosphorylation and dephosphorylation are a couple of the most common ways of activating and deactivating enzymes, right? It's not uncommon for, in a metabolic process, for an enzyme to have an amino acid residue that will get a phosphate added to it, and then later on have it cleaved. And so the phosphate almost acts as an on-off switch, right? It can become more or less favorable when it's phosphorylated, and then the opposite when it's dephosphorylated. Some of these are more sensitive to this than others. Serine, threonine, and tyrosine are really sensitive to this because they all have available OH groups. And the OH groups can react with phosphate sources like ATP to form phosphate esters. So let me highlight a couple of these. You've heard of this guy. This is the sodium-potassium pump. You've probably heard of this since high school biology, right? Sodium-potassium pump. Fun fact, it's not a physical pump. Sodium-potassium pump is actually an enzyme. It is a type of ATPase. All right? And so basically what this does, the sodium-potassium pump is an enzyme that sort of regulates the flow, the concentration, internally and externally of sodium ion and potassium ion. More specifically, it's there to regulate extracellular, outside the cell, concentration of sodium, and intracellular, in the cell, concentration of potassium ion. All right? And so there's the diagram of the sodium-potassium pump, and you can sort of see what happens here to that ATPase as you get phosphorylated or dephosphorylated, right? So if you look in the top left corner where you have the E in sort of the more flat oval shape, regular oval shape, it can have a reaction with ATP, right? ATP can lose a phosphate group, and this phosphate can get attached to your enzyme, your ATPase. And that causes a conformational change that allows 3 of your sodiums that are inside the cell to escape. Basically, you're quote-unquote pumping them out, right? It doesn't do this with a dephosphorylated enzyme. It only does it when the enzyme is phosphorylated, right? That phosphorylation, that phosphate group is an on switch for this. All right? Then, if you go down to the next portion here, that enzyme can then be dephosphorylated, right? It can be hydrolyzed, reaction with H2O, and you can cleave the phosphate off of that enzyme. And when that happens, that enzyme can then change conformation back to its original form, and in the process, it can carry two potassiums from the outside of the cell to the inside, right? So you have this consistent cycle of phosphorylation and dephosphorylation that occurs that allows the enzyme to adopt different conformations. In one conformation, it transfers sodium inside out, and in the other conformation, it transfers potassium outside in. And it just keeps consistently going in this little circle. All right, another example is glycogen phosphorylase. All right, glycogen phosphorylase is an enzyme that catalyzes the initial step in the breakdown of glycogen. We'll go over this in the carbohydrates chapter, but glycogen is a polysaccharide, and it's basically how the liver stores glucose, right? It can store glucose, and then when we need glucose, a signal is sent for glycogen phosphorylase to go into the glycogen chain and cleave some glucose off for us to use, right? So this one is interesting. This is interesting because this one actually has a couple of different levels of control, right? It's controlled both by phosphorylation and by external activators and inhibitors. So basically, so you can see it in this photo right here. Just look at that top part there. We have actually two forms of glycogen phosphorylase. We have phosphorylase B and we have phosphorylase A. All right. Phosphorylase A is the more active form. Dephosphorylated is less active. Both of them can be completely active. Both of them can be completely inactive. Phosphorylated version has more of a tendency to be active, though. All right, so if you look in that top line, there's an equilibrium between A and B. And this is controlled by another enzyme, by two other enzymes. Phosphorylate kinase, that's the one that adds phosphate to glycogen phosphorylase. And then, sorry, I'm trying to read this. Phosphoprotein phosphatase 1. That's the one that dephosphorylates glycogen phosphorylase into the B form. All right, so at the top here, both of these are inactive, right? Both of these are in the T state, right? If you look down below, each of these can be activated, all right? Phosphorylase B can be converted from the inactive T state to the active R state. What does this? Well, if you look at the equilibrium arrow going to the active site, active state, AMP, that's adenosine monophosphate. So if you have a high presence of adeноmonophosphate, AMP, it will take this phosphorylase B from its T state to its R state. And that means it can be active. It can do its job. However, that active R state can also be inhibited. It can be inhibited by several things: ATP, glucose 6-phosphate, glucose, or caffeine. Right? All of these will convert the active R state into the inactive T state. All right, then you have phosphorylase A, right? And its inactive T state. It can bind a substrate and actually be converted into the more active R state, which conversely can be inhibited by glucose and caffeine. Right? So this is complicated. You're probably sitting there with a confused look on your face. You'll probably have to go through, read this multiple times, listen to this multiple times. Basically, glycogen phosphorylase is a more complex enzyme because it has multiple levels of control. Phosphorylase B, phosphorylase A, the difference between those is a phosphate group. right? Phosphorylase A is a little bit more active. They can both be completely inactivated or completely activated by other external inhibitors or activators. All right, so try to digest that. I'm going to end this video, and then we'll pick up the rest in a part 3. All right, have a good one. I'll talk to you later. Bye-bye.